Third criteria, it is extended conjugation. What I mean by this extended conjugation? Let us take benzene. I make this bond somewhat thick. This is the another resonance structure. The thick bond is here now. Then further I can go like this. In that, the thick bond will be here. I can go like this, and if I compare all the resonance structures, this thick bond will delocalize on all the carbon atoms. So that is called extended conjugation. That is not possible if there is any sp3 carbon in the ring. For example, this carbon, it is sp3. This also it is sp3. Not only because of this carbon, you can even compare. The extended conjugation is not possible. The plus charge can fall here. Take this cation, cyclopentadienyl cation, indicate like this. In this, that's all. If you draw the resonance structure, you will get plus charge here. Then here, further on this carbon, so now the plus charge is present on all the carbon atoms. You can see that very clearly here. So on all the carbon atoms, you can find the plus charge. So not only delocalization of double bond, you can compare this positive charge also. Similarly, you can go for minus charge. If you draw the resonance structure, this minus charge will be on all the carbon atoms. That's why we write like this. One more thing. Lone pair of electron. This lone pair of electron also can involve in extended conjugation. But when it involves in extended conjugation, what you get is a localized positive charge and a minus charge which can be delocalized on all the other carbon atoms. So that also is possible. Now it is similar to cyclopentadienyl anion. The last criteria is number of pi electrons involved in delocalization. Let us go for some example. First one, compound which has only double bond. There is no problem at all. What is the number of double bond? Multiply by 2. So it will be very easy. If there is any positive charge on the molecule, it will not contribute to pi electron. You have to consider only the double bond. So here there are 3 double bonds. there are only 6 pi electrons. If there is any minus charge, then the minus charge will contribute 2 pi electrons. So here there are 6 pi electrons, 4 from the double bond and 2 from this minus charge. If there is heteroatom with lone pair of electron, it may be nitrogen, sulfur, oxygen, phosphorus, selenium. All these atoms have lone pair of electron. So they can contribute 2 electrons for the molecule to attain aromaticity. So this lone pair of electron is equal to 2 electrons. So here we have 2 double bonds, so it accounts for 4 electron plus 2 more electron on nitrogen. So total there are 6 electrons. Interesting thing is comparison between this molecule. First one, it is pyrrole. I mentioned the lone pair on nitrogen gives 2 electrons for the molecule, so it becomes aromatic. What about this pyridine? Already there are 6 electrons. There are 3 double bonds, so there are 6 electrons and 2 more electrons from nitrogen. So the total should be 8. That means, is it anti-aromatic? No, it is not anti-aromatic. The nitrogen on the pyridine will not give 2 electrons. The reason is, this is the structure of pyridine. The lone pair of electron is here. The pi electrons are like this. So the lone pair is in an orbital which is perpendicular to the pi orbitals. So this cannot involve in overlapping with this. So it cannot contribute. In simple sense, I can say if there is a system like this, if there is no hydrogen or methyl group or alkyl group attached to the nitrogen, that nitrogen cannot contribute to aromaticity. That nitrogen cannot contribute lone pair of electron to the molecule. I can go for several examples like that. So this is imidazole. This will give 2 electrons, that is lone pair of electron. Even though this nitrogen has lone pair of electron, that will not participate in the overlapping. I can go for pyrazole. Here also the same thing. This nitrogen lone pair will not involve. I can go for this compound also. There are 2 nitrogens and there are 2 lone pairs. It will not contribute. Only when there is NH or N alkyl group, that will contribute. In the other hydrocyclic compounds like thiophene, this lone pair of electron can be given to the compound. Similarly, this one, Even though there are two lone pair of electron, only one will be given for aromaticity. What about the aromaticity of heterocyclic compounds? Most of the heterocyclic compounds, what we generally come across, are aromatic in nature. For example, let us start with pyrrole. The number of electrons involved in the delocalization is 6. So this is aromatic. What about this one? Already there are 6 pi electrons. In addition to that, there is a lone pair of electron. So the total number of electrons, it should be 8. Is it anti-aromatic? No. This is also aromatic. The reason is this lone pair of electron is in the orbital which is perpendicular to the pi bonding orbital. So this lone pair cannot overlap with this one. Only these electrons involved in delocalization and only 6 are there. So it is aromatic. Easily you can remember, if there is a system like this, double bond N, and there is a ring and conjugation is there, then this lone pair of electron will not involve in delocalization. You can go for system like this. This lone pair of electron will involve in delocalization. On the other hand, this lone pair of electron will not, because it is like this. Not only nitrogen, you can take oxygen also, furan. Similar to nitrogen, this also can give lone pair of electron. There are 2 lone pairs of electron, but only one will involve in delocalization. So it will be 6 and it will be aromatic. Here is an interesting problem. That is, furan and pyrrole. If you treat this with a dienophile, let's go for maleic anhydride. Furan will react with this to give the addition product, Diels order addition product, but pyrrole will not give. What is the reason? Both are aromatic. So when it undergoes Diels order reaction, this aromatic compound becomes non-aromatic. Then what is the driving force for this reaction? Why it takes place? On the other hand, pyrrole doesn't react. What is the reason? Another type of compound is fulvene and fulvalene. So this kind of compounds are called fulvalene. A conjugated polyene is connected to exocyclic double bond. The same thing if you attach another ring, that is called fulvene. What about this? The same compound if it exists like this, then this ring becomes aromatic. So this is the driving force for this molecule to exist partially ionic. It is not completely ionic, but there is some ionic character for this. Because of this, the dipole moment and polarity will be high. If you consider this molecule, the dipole moment will be very low. But when you go for this one, the dipole moment will be very high. If this molecule exists like this, then the dipole moment should be very less. If you consider this ionic form, then the dipole moment should be very high. Similarly, polarity also should be very high. It has been observed that the dipole moment of this compound is higher than the calculated for this because of this structure. I can go for one more fulvene. Consider this compound. If it exists in this ionic form, then we get two aromatic rings. So this is aromatic, this is cyclopentadienyl anion analog, this is trophylium cation analog. So both the rings becomes aromatic. Because of that, this fulvene prefers to exist like this. So the dipole moment and polarity of this compound will be very high. Compared to the earlier one, the polarization will be very high for this compound. The next compound, it is squaric acid. The name of this squaric acid derived from square. So since the structure is square, it got this name, squaric acid. If I remove this proton, then what I get is compound like this. So this proton is highly acidic because of that there is conjugation, and you may know there is plus here as well as here. So it is equivalent to this moiety dication. So this is aromatic in nature. Because of this, the acidity of this proton will be very high. Even a weak base can take this. Not only this proton, even this one, even after forming the anion, further this proton can be taken by base. So both this as well as this protons are highly acidic in this squaric acid. So it is a special type of compound which exhibit aromatic character. There is one more type of compound like this, that is known as signone. Basically it is heterocyclic compound in which the nitrogen has positive charge and the minus charge will be outside. So number of electrons in this, easily you can calculate, it is 6. So it is aromatic in character. It has aromatic character. Now let us discuss about the aromaticity and the character of the compound. How does it affect the character of the molecule or the property of the molecule? Here, I would like to discuss about 4 topics. The first one, how does it affect the physical property? Chemical property, spectral property. What is the effect of aromaticity on these things? Again, when you go for physical, I would like to discuss how does it affect the structure of the molecule. How does it affect the acidity of the molecule, acidity of hydrogen in the molecule. Here itself we can discuss about pKa also. Last one, dipole moment. The spectral property, I would like to explain about the proton NMR value. How it is affected because of the aromatic character. Last one, the chemical property, how the chemical reaction is driven by the aromatic character. First, let us go to the physical property. First one, it is structure. Already we have discussed about that. This cyclooctatetraene, this exists in this form. The reason is this is anti-aromatic. It is not because of ring size, it is very big. No, it is not the reason. Since it is anti-aromatic, it prefers to be like this. Even 12 and 16 member also, they are not planar. The reason is they are anti-aromatic, so they lose its planarity, thereby it becomes non-aromatic. To the same molecule, if you add 2 electrons, then this will become aromatic. So it is planar in structure. From this, easily you can realize that it is not the ring size. It is because of aromatic character, it becomes planar or tub shape. If you go for 14 aniline and 18 aniline, they also planar because of the aromatic character. The second one, acidity and pKa value. You may know that acidity and pKa value, they are inversely proportional. If the acidity is very high for a particular proton, then the pKa value will be very less. Let us take these 2 compounds. This is cyclopentene, this is cyclopentadiene. This proton is highly acidic than this one. The reason is, if this proton is taken by a base, then what we get is cyclopentadienyl anion, which is aromatic. Here it is not aromatic, but here it is aromatic. This is the driving force for the acidity of this proton. On the other hand, if you add base to this, it will abstract, but what we get is non-aromatic compound. It is not highly acidic because we are not getting aromatic compound. So this also non-aromatic, this also non-aromatic. What about this compound? If I add a base, you can find this proton, it is in the alpha position to carbonyl group, so it is expected to be acidic. But if the base abstract this, then what we get is this system. I write in the enol form also. Now this is anti-aromatic. This one, it is non-aromatic. The non-aromatic system, because of enolization, because of abstraction of proton, it becomes anti-aromatic. So this for reaction is not preferred. I won't say it won't work. It is not preferred because of this one. So the acidity of this is less than the expected one. The third property, it is dipole moment. You may know dipole moment, it is nothing but the multiplication of charge and the distance between the charges. Generally, this question is asked in fullerenes. Let us consider this fullerene. If this exists in ionic form, both the rings becomes aromatic. Because of that reason, the molecule ionizes and exists in this form. So the dipole moment will be very high since it is ionic. I can go for one more compound, that is nothing but azulene. So it is like a naphthalene. The only difference in naphthalene, both are 6 member, but here 1 7, another 1 5. One may expect that the polarity of this and naphthalene should be almost same, but when we compare that, there is lot of difference. The reason is it prefers to exist in the ionic form like this. So because of this ionic form, the dipole moment will be very high and the solubility will be there in water to some extent. The second one, it is chemical property. Let us consider these two molecules. The earlier one, it is aromatic, so there is no doubt about that. What about this? This is anti-aromatic. In fact, this is not that much stable one. If I reduce this by lithium aluminum hydride or sodium borohydride, the rate at which it proceeds and this one, if you compare these two, the rate of this will be very slow. On the other hand, this will be very fast. The reason is, once it is reduced, we get the corresponding alcohol. This one is non-aromatic, this also non-aromatic. From anti-aromatic to non-aromatic is more favor. On the other hand, from aromatic to non-aromatic it is not that much favor. That is the reason. I can go for one more example. Consider the elimination in this substrate. When it gets eliminated, what we get is benzene. When it gets eliminated, we get cyclobutadiene. This is aromatic and this is non-aromatic. Sorry, this is anti-aromatic. So from non-aromatic gets converted into aromatic. So this is more preferred because this is more stable and it has less energy. On the other hand, from non-aromatic to anti-aromatic, it is not preferred. So the reactivity is controlled by the aromatic character. If there is any possibility for the molecule to become aromatic, that reaction will be preferred. If the aromatic character is destroyed in the reaction, that reaction is not preferred. I won't say it will not proceed, but the reactivity will be very slow. Let us consider this molecule. If I add H plus, what will happen? Whether it will add here or both, nitrogen will undergo protonation. That is, the first one like this, second one like this, third one, both gets protonated like this. Which one is more facile? In other words, I can ask what will be the basicity, what will be the pKa value of this. So that also may be asked. Look at this. Only the lone pair of electron on this NH involves in pi orbital overlapping. This one is free. So this will not participate in that. So what happened is this takes the proton, this will not take the proton. So what we get is this product. Sorry, here it is plus. If this nitrogen takes, then what we get is anti-aromatic compound. The aromatic compound becomes anti-aromatic. That is not favored. You may know that in benzene there will be ring current and it will be like this. Say this is the applied magnetic field. And this is the hydrogen. Now, under the applied magnetic field, the direction of the ring current will be like this. That means, at this region, the applied magnetic field and the direction of ring current, they are in the same direction. You can see here, it is in the same direction. So, the magnetic field experienced by this hydrogen is higher than the applied magnetic field. Because of the ring current also it experienced some magnetic field. So, the magnetic field experienced by this is more than whatever we have applied. Look at this center, this region. So it goes like this. Here, the applied magnetic field and the ring current, they are in opposite direction. So since it is a circle, you can see at the peripheral, it is aligned with the applied magnetic field, but at the middle, it opposes the applied magnetic field. So the protons, whatever is here, that experience less magnetic field than the applied one. That affects the NMR behavior. You may know that for simple olefin, this delta value will be between 4 to 6. It depends on the substituent. So generally it will be between 4 to 6. In benzene, there is only double bond. So you may expect this to appear at 4 to 6. But it is not so. It appears at 7.5. Depending on the substituent, it may go from 7, from 6.5 itself it will start, 6.5, even 8.5 it will go. So that is because 7.5 it is downfield. Compared to this is upfield. Since some magnetic field, since there is some ring current, because of that it is going downfield itself. Now the question is, take this compound. These two hydrogens will be in the middle of the ring. So you can see here, it will be here. Since it is allelic proton, it is expected to resonate around 2.2. Generally allelic protons will appear around 2.2. But because of the ring current, this will be in minus value. Because in the middle, the applied magnetic field and the ring current, they are opposing each other. This is one example. I have few more examples. Take this. This is 14 aniline. It satisfies 4n plus 2 rule. So it is aromatic in character. So it is planar. What about the hydrogen here? They are in the middle. So ring current goes like this, and the hydrogen, they are in the middle. So they also will be in the upfield. Since it is aromatic compound, it should resonate around 7.7 to 8. But these protons will be in the upfield compared to these hydrogens. The value is appreciable change. If this is around 7, this may be, I have no idea, you have to refer the book. It may be around 3 or 4, even sometimes it may go in negative value. You have to check that. For the same reason, in cyclophane, a compound like this, you may know, you may have come across cyclophanes. Basically, it should not come under aromaticity. Since we are discussing about this property, I give this as example. This CH2 is just above this ring. Because of that, this will be in minus value. On the other hand, this CH2, since it is not above the benzene ring, this will be around 1.2 something. Because of the ring current whether it is opposing or it is aligning with the applied magnetic field, we get different spectral data, spectral value. Here I have some interesting problems. First one, arrange the above compounds in the increasing order of their proton NMR delta value of hydrogen atom, which has been mentioned here. 3 compounds has been given. This one is aromatic, this is allylic proton, this one is aliphatic, there is no double bond here. Arrange them in the increasing order of their proton NMR delta value. Second one, this N-methyl imidazole. With this, I add 2 equivalent methyl iodide. What will be the product? Even if I add 2 equivalent, methylation takes place only on this nitrogen or this nitrogen, that is the second option. Both the nitrogens undergo methylation to give this product, that is third one. Fourth one, methylation takes place on this carbon and this carbon. Because of the resonance, you can find that here, this proton is acidic, so that undergoes methylation. So I have given 4 options. Which one is correct? If this compound is treated with metachloroperbenzoic acid, what will be the product? First one, nitrogen gets oxidized to N oxide. Second one, epoxidation takes place in this double bond. Fourth one, epoxidation takes place in this double bond. Third one, it is hydroxylation. So because of this, electrophilic oxygen is attacked by this to get this compound. Which one is correct? The fourth problem, when this anthracene, which has methyl group here, is treated with benzene, it undergoes 4+2 cycloaddition. What is the product? Which diene undergoes 4+2 cycloaddition? The first option, this diene. The second option, this diene undergoes 4+2 cycloaddition. This diene is the third one. If it is anthracene, then we may get only 2 options. This and this will be identical. Now, since we have methyl, there are 3 different types of diene. The fourth option, it is mixture of products. We can't say the benzene may add here as well as here or here. We may get mixture of products. Which one is correct? Next one, I have given 3 compounds. The compound that can be readily oxidized by active manganese oxide and cannot be readily oxidized or respectively. In this, which one will be readily oxidized, which one cannot be oxidized? So if it is oxidized, what we get is anti-aromatic. If this is oxidized, we get non-aromatic. If this is oxidized, we'll get aromatic. Based on that, you have to predict. You may know that allylic alcohol can be oxidized by MnO2. Three compounds has been given here. Arrange the above compounds in the increasing order of their ability to enolize. Which one will undergo enolization faster? So what will be the order of the rate of enolization? Next problem. Arrange the above compounds in the decreasing order of their ability to undergo reduction. Which one will undergo reduction easily? That you have to predict. Arrange the following in the increasing order of their heat of hydrogenation. Some of you may know what is heat of hydrogenation. It is the heat released during hydrogenation. So which one what will be the order of heat of hydrogenation? Here I have given a hint also. Heat of hydrogenation is inversely proportional to stability. So you may know which one is more stable based on the aromaticity. Then you have to go for the inverse one. The next problem, arrange the above compounds bracket hydrogen in the increasing order of their acidity. Sometimes it may be asked pKa also. Acidity and pKa are inversely proportional. This hint I have given. So you have to arrange in the increasing order of their acidity. That will be decreasing order of pKa. Next problem, arrange the above compounds in the increasing order of the reactivity towards Diels-order reaction. Which one will react faster? Next one, which of these compounds will give precipitate on heating with silver nitrate? I have given 3 bromides. First one, cyclopropenyl bromide. This cyclopropyl bromide. This also cyclopropenyl, but bromine is the double bond. Which one will give precipitate on heating with silver nitrate readily? Next one, the compound that undergoes elimination readily is, I have given 4 compounds. In this, which one will undergo elimination readily?